Hi everybody, I'm Konstantinos. Today I'm going to talk about Shifter, a space efficient value iteration for finite horizon NDPs. Enjoy and work with Ioannis, Sadek, Verena, Michalis, and Panagiotis. Reinforcement learning is a type of machine learning that focuses on decision making and control problems. Using applications like resource management, gaming, robotics, accommodation systems, and many others. Usually an agent interacts with an environment and learns to try and error. The agent can be a robot, the environment can be a maze, and the goal of the robot could be to find the path and exit that maze. And we manage to do that by executing some actions and getting reward, feedback, and use this information to learn and exit the maze. You can describe the problem as an MDP, a Markov decision process, that's a tuple M with countable number of states. You can think the states that's where the robot can go. Here we have a toy example with 4 states, a grid with 4 locations, actions, what the robot can do. Here in this example, again, from S0, the robot can only go east or south. The transition probability is P. As the model is probabilistic, the environment is probabilistic, then the agent tries to perform an action. In this scenario, from S0, it wants to go east, but with 0.8 probability will end up to S1. It can end up to S2, that's a state that it didn't intend to go. The rigor is the feedback, how good an action it is. The horizon N is there is a limited number of steps, actions, let's say, that the agent can take. And the goal is to find a policy P, that's a set of actions, that maximize the cumulative rewards over the horizon. There is an algorithm that allows you to find the best action for every horizon step for every state. That's called value iteration for finite horizon NDP, and standard solution in the literature, where with a Bellman equation to define the value of the state, let us know how good a state it is for a specific horizon step, and this is just simply by greedily taking an action plus the remaining trajectory from that action. And the best action from a state is the policy, and the value you get is the value of the state. But the difficulty here lies to that we cannot calculate the remaining trajectory, the future rewards. So we can start from something we can solve where it is for one remaining hop, we have no remaining trajectory. So we can just get greedily the best action and use it as the value of the state and the policy for horizon 1. And then use this value of the state as the remaining trajectory, or for 2 remaining hops, we can greedily get 1 step plus the remaining trajectory because we previously calculate another hop. And then we can use it recursively for the calculate the 3 hops. We can use what we previously calculated for 2 hops and so on up to k hops, where at the end we have the policy for every state and every horizon step by doing that recursively. And we will need to store this policy in a table where we have for every state, every horizon step, the optimal action. Then when we start executing action, we just go to the table, get the optimal action, and execute it. But what happens if we cannot store the full policy memory? And then we have to run the in-place solution. It has no memory requirements over the horizon, where when we need to execute an action, we're dynamic programming from horizon n1 up to n, execute the action. We do not store anything in the memory, then we need to calculate the next one on demand again, n-1, then start from 1 horizon up to n-1, run program again all these steps, and execute the action and so on, and repeatedly do that. And as you can imagine, this has an effect on the runtime. It becomes quadratic on the horizon, as it makes it difficult to run for an horizon length. On this study, we noticed the trade-off between runtime and memory of the two solutions in the literature. So, and we acknowledge that resource-constrained devices exist like mobile devices or IoT devices, and they will not maybe not be able to fit the full policy memory table in their device. So we propose a solution that stores strategical checkpoints for specific horizon steps, the value of the states, and the policy, where you can do calculations from these checkpoints up to the horizon you want. That would be closer than starting from the beginning, these calculations. That allows us to reduce the runtime while keeping the correctness, because we just do recalculations, and as dynamic programming is deterministic, then we provide the same results over and over again. And we provide two solutions that allow us to reduce the memory complexity with high runtime trade-off and solve problem. The first one is a radical solution, where we store only square root n checkpoints every square root elements. We run dynamic programming from the beginning again up to horizon n. This is, let's say, example with horizon n16. And we will store only checkpoints for 4, 8, 12, and 16 every square root n elements. And then we also keep the intermediate values in the memory for the active tables, and then we erase it after executed. What do we mean? Let's say we execute the policy for horizon 16, and then we need to calculate for horizon 15. Then the active tables will be 12 to 15. So we start running dynamic programming for 12 to get the values for 15, but we will keep in the memory the values, the optimal policy for horizon 13, 14, and 15. That will increase the space complexity to 2 square root n, but it will avoid 2 recalculations in the intermediate values. And as you can see, the total complexity of this algorithm is exactly 2 times lower. It stays the same, the complexity, because we will do the calculations only another one time, and the space complexity reduces to square root n. We decided to reduce even more the memory by a logarithmic factor, where we imagine that we have a binary search tree. I said imagine because we still have a stack. But to decide if we store an element, we use this binary search tree. And the binary search tree is the root of the tree is in the middle of the horizon, and the left child is in the middle of the first half of the horizon, and the right child is the middle of the right half of the horizon, and repeatedly so on, the values. And the keys on the tree, the nodes, are the horizon. And when we mean horizon, we're talking about remaining hops, just to clarify again. And this idea is to store the path from the root to the destination only to the stack, and you see this information to the recalculations. This, of course, because the tree, binary search tree, is bounded by the height, that's log n. That's the space complexity, and the runtime, because of the recalculation we will do, you will see next how that goes, increases to a logarithmic factor. To run an example, again, we run dynamic programming for remaining hop 1 up to n, and we decide if we keep a node if it's in the path from the root to the destination. And as you can see on the first half here, nothing will be on the path to the destination as we start from the root. And the path from the root to the destination has only nodes 8, 12, 14, and 15 signed, as everything on the left path, the left side of the tree, will not be found in any binary search or in the path here to the destination, as you can see. And then we start executing action normally. After we run one dynamic programming, and we have these checkpoints. 15 is in the memory, 14 is in the memory, so the first node we care about is 13. We need to do the calculations. Then we go to the top of the stack, it's the node 12, and we can use this to get the value, the policy for remaining hops 13, horizon 13, to execute the actions. Then we execute the actions for 13, 12, and then we need to do the calculations for the node 11. We have a checkpoint only node 8, so we have to start the dynamic programming for the horizon 8 to go to 11. And you can see that 9 is not the path, 10 and 11 are, so we keep only this node to the table. And then we execute the actions for 8, 11, 10, and 9. We do what do we do for 15? We go to the top of the stack, it's node 8, so we can start from again 8 to get for the node 9. So the next interesting point is that what happens if we want to calculate for the nodes for horizon 7? We have nothing in the memory, we have no checkpoints. What we do, we treat it as a new tree. We start again from horizon 1, one remaining hop, up to 7 now, and we keep again the path to the node 7, like this 4, 6, and 7. And we repeatedly do that over and over again. We check if it's in the path, we store it, otherwise we ignore it, and so on until we execute the policy for all the nodes. And we implemented our algorithms in C++ and open source. You can access the code by scanning the QR code have two MDPs with their variations. The first one is Elastic Computer Cluster, that is a distributed cluster. As a company tries to handle work and user-generated workload without using too many resources, too many VMs, and tries to find balance how to do that. And the reverse stream have the MDP here, where on the left you have low, easily accessible rewards, and on the right you have more difficult but higher reward. So the swimmer, let's say swimmer trying to swim across the river, has to choose what to do every time. And we evaluate the memory and the runtime because we want to leave what we expect theoretically will happen in practice, and we evaluate rewards based on the comparing to approximate solutions, like the stationary policies. The one is a turnpike, we name it, is the policy you get after you run dynamic programming, and it's the last row of the table for horizon n, and you keep repeating that. And the value iteration for infinite horizon, the discounted, where you use the gamma value to make the future rewards count less, and it converges based on this gamma value. And on the memory and runtime experiments, we can see now on memory the stationary policies uses only that do not use any memory, where the logarithmic from the exact solutions has less memory, and you can see when the horizon increases, it has small increment in the memory as we expected, where the radical has a slow increment and the standard increases linearly. And on the runtime, it would be expected like the in-place could not run for high horizon is really slow because of the quadratic factor. The approximation, as we said, is not based on the horizon, so it's a straight line. And the three algorithms, the standard solution is the fastest as it has no recalculation, it's a big solution. The radical is 2 times slower, so it's a bit slower here. And the logarithmic, again, is slower from the radical as the horizon grows because of the logarithmic factor. And you can see them compared in the reverse stream example, where you have the memory and the execution time in one graph, and the horizon, you can see it in the markers. And the standard is higher because it has the more memory, but it's in the left because it's the faster. Radical is in the middle, it's in between these two. It has memory needs, but it is faster. It is relatively fast, where the logarithmic is a bit slower, but it has really, really low memory needs. And on the rewards, we can see again what we expected. In some MDPs, in Makeover Fast, like the Elastic Computer Cluster, you will be able to use stationary policies and get really good rewards, like the exact solution. But if you have a stationary, non-stationary rewards, like the variation we did we gave raw Rombi rewards, for every horizon and different state, you will get bonus rewards. You can see that a stationary policy cannot work well, and the higher the rewards will give as bonus, the ratio between the exact solution and the stationary solution are really, really low. You lose a lot of rewards. And on the reverse stream example, again, the reward ratio drops in specific horizon steps, and it is where the swimmer has to make choice, and where the decision is difficult. And you can see how many rewards you can lose if you choose a stationary policy. But this is the rewards are significantly low if we consider the variation we did. At a small change in just to remind you, the reverse stream you can drop back with 0.05 probability to the previous state. We make the 0.04, and we make with 0.01 probability to drop further back to half of your position. And this makes the model not to be able to converge, and you lose a lot of rewards on that scenario. So what we did in the study, we show that you need a non-stationary policy. It benefits you a lot. And we show you solutions to use non-stationary policies for resource-constrained devices and high horizon. Especially we lower to a logarithmic factor where you can run to almost any device with low runtime trade-off, and we provide solution that is generic and it's easy to implement.